Okay. Well, this is section 1232, the PM section. I also have an AM section. Sometimes, sometimes there's space available in the AM lab. So if something happens, let's say you miss a lab, you need to make something up, you might be able to come to both the AM and the PM. That way you might be able to make it up. Some labs, there are no makeups. They're doable. But we look at it case by case. I'm the instructor for the course, Robert Chabot. I got my bachelor's in chemistry from UCLA and my PhD in chemistry from UCSB. I didn't start at UCLA though. I started at Santa Barbara City College as a geology major. And so as a geology major, you take like physical geology, historical geology, and then mineralogy. And when I hit mineralogy, then I was thinking, maybe I'll switch to chem. Because chem seemed more fundamental, like science. In mineralogy, we try to identify minerals. You try to identify minerals by the shape of the crystals, the color. Color is very deceptive. And so in mineralogy, we carried a porcelain plate, which looks something like this. And then you take the mineral and you scratch it. Are you in this class?
I was going to try to add it. Is there any room in the middle?
Well, there's some seats available, but if there are some no-shows, then yeah, there's room. But if there's no no-shows, you can take it for now. So, to compare colors, you should compare colors of the same crystal size. So what you do is you scratch the crystals on here to grind them up into fine powder, and then you compare the colors of the powder. Because the color depends on how big the crystals are. So if you look at big salt crystals, they're totally transparent and colorless. Whereas if you look at small salt crystals, they look white. And so we need to get it into fine powder, and then you can do a fair comparison. But when you're looking at the crystal shape, the color, it just didn't seem like, it seems subjective, somewhat subjective. So, some crystal shapes are very distinctive, others aren't. And so I thought chemistry seems more fundamental, but that was a little premature in changing my majors because the geologists also use instruments to analyze things as well. And so if I just stuck with it, and in fact, you'll see a lot of blend over. When I was at UCSB, I was working in the materials research laboratory. The materials research laboratory consisted of biologists, geologists, chemists, engineers, looking at different materials. And the distinction starts to fade. Are you a geologist or are you a chemist? There are a lot of geologists that are doing things that chemists would normally do, and vice versa. And so those distinctions begin to blur. And so that's anyway. Just to interrupt here. If you came in late, I have a couple of, actually not a couple, just one sheet. You can grab one of these and fill it out here. That way I can know how many I have, how many I can add. So grab one of those and tell me what you're trying to do. All right, so at Santa Barbara City College, I changed my major to chemistry, and then I transferred over to UCLA and finished up my bachelor's there. I'll talk more about that. Okay, on the canvas, if you're trying to add, you probably don't have access to that. But I posted module 1. Which is week 1. Yeah. And so I have the first 3 chapters of homework here. Homework won't be due for a while, but you'll want to start this. Some of these problem sets are pretty long. like chapter 1. Especially these latter problems are time consuming. Let's take a look at the course. You can download this as a PDF. I already did that. Let's do that here again. This file. All right, my office is just down the hall here. It's in room Chem 120. You can reach me either there or by email or phone. My extension is 3240. This is dial the campus line. The office hours, I haven't quite finalized those yet. I'm thinking my office will be on Tuesdays, before my morning class, which my morning class starts at 11:30. So maybe at 10:30 morning, and then after my afternoon class or before, we'll take a look, see how the schedule works out. And then maybe an online one on Monday. So we'll fill this in later. All right, the catalog course description, we're looking at just the principles of atomic and molecular structure and chemical interactions, et cetera, et cetera. There's a dictionary definition. In the dictionary definition, I like this definition number 2, but I would have modified it. And maybe definition number 1. Definition number 2 is a bit too narrow. It's the composition, structure, properties, and reactions of a substance. What's a substance? Do you guys recall what the substance is? Maybe the break is a little too long. Substance. How would you define a substance? Yeah, element or compound. Usually substance is pure. It's got fixed properties, fixed composition. And so there are 2 types of substances. You have the elements and the compounds. Versus what? Versus, if it's not a substance, then it's a mixture. In that case, I don't know if I want to be that strict, because a lot of people believe, well, mixtures are substances also, like hydrochloric acid. Hydrochloric acid is a mixture of water and HCl. Technically, you wouldn't call that a substance; it's a mixture, but hydrochloric acid just seems like a substance as well. And so the chemists are kind of strict on how they define things. And so this definition is a little bit too strict, because chemists not only study elements and compounds, they also study mixtures. And then also chemists have a little bit different definition of properties. When a chemist thinks of properties, there are 2 types of properties that come up. What are the 2 types of properties chemists are interested in? 2 types. Physical properties. Give me some examples of physical properties. Color. This one. Shape. The crystal shape. That's what we try to identify the minerals using. We try to identify the minerals using physical properties. The color, the shape. Although it's hard to do this in the field, but there are other properties that we could if we had some tools. There's a chair right there. Are you registered in the class?
Yes.
Okay. Here's a sheet. All right. I thought we could add everybody, but now we don't have enough seats. I gave up my seat there. So unfortunately, if you're last on the list, you might not. Or even, I don't know how many no-shows are going to show. So maybe nobody on the wait list. Hopefully, we'll get some of you. But examples of physical properties would be color, shape of the crystal. What else? The size, the smell would be another. The size, yeah, you know. But is that a characteristic? Like water always has a certain size? No, we use the properties to characterize substances. So water is a substance, but there's going to be a size of the molecule. So if we're looking at the molecule, yes, then size would be important. Can you think of any others? Volume, like say, does water always have a volume of 1 gallon? No, but the water molecule does have a volume. And so volume, yes, that's a physical characteristic, but it's not something that is unique to being water unless you're at the molecular or particulate level. But, volume is related to something. Mass and volume are related. What are mass and volume related to? Density. So density is something that's unique to water. Do you know what the density of water is? A lot of people haven't memorized. Do you have it memorized? 0.92 is a little low, a little higher than that. 1.01 is a little high, lower than that.
Just water?
Yeah, just to 1 sig fig. Usually people memorize it at 1 or 2 sig figs. It's 1 or 1.0. But if you get to 3 sig figs, it's like 0.99 something. And so it's about 1. That's a characteristic of water. That's a physical property of water. The physical property of water is its density. Its density is about 1 versus gold. Do you know what the density of gold is about? How many times heavier is gold than water? 20. Yeah, it's about 20 times heavier. So if you have a gallon of water, it weighs about 8 pounds. If you have a gallon of gold, it would be 20 times 8 pounds. It would be like 160 pounds. Right? And so a gallon of gold, which would be nice to have, of course, it would weigh a lot. As much as a person. All right, so that would be another physical property. Other ones would be melting point, boiling point, etc. In addition to physical properties, we also have what? Chemical properties. Now, this is the distinction here because this is saying the composition, structure, properties, and reactions. Well, reactions are chemical properties. And so chemical properties are what types of reactions does it undergo. So in geology, what we used to carry is a little squirt ball. And the squirt bottles are just like those. But it's filled with not water. Do you know what it's filled with? Not distilled water. Well, there is distilled water in there, but it's a mixture. HCl. It's filled with hydrochloric acid. And what you do is you go around and you squirt the minerals with hydrochloric acid, and if they start to fizz, then you know that's a carbonate-based mineral. If it doesn't, then it's a non-carbonate-based mineral. And so you can easily tell if it's carbonate or not carbonate by reacting. That would be a chemical property there. And so here, a chemist would just say composition, structure, properties, get rid of this reactions, because reactions are included in properties. Not a substance, but we study a lot more than just elements and compounds. We also study mixtures and whatever else. And so that's why definition number 1 might be better. The science of the composition, structure, properties of matter. And so matter is this all-encompassing thing. Matter, how do you define matter? Anything with mass that occupies space. So this is just a physical material of the universe. And so this is probably better then. But this is saying especially of atomic and molecular systems. Well, we don't need that. It's just probably just the science, composition, structure, and properties of matter. So that's what chemists do. So the course objective, you can read through here. Basically, just learning all the material in the course. But upon successful completion of this course, students will have a chemistry background comparable to that obtained at a CSU or UC campus. So that brings us to our book. This is the textbook for the course here, Petrucci, 11th edition. Actually, when I was in general chemistry, I used Petrucci also. It's more like the first edition, Petrucci. Actually, they don't update this very often. So it was, I think it was like the 8th edition. This one was published in 2017, but it's still pretty relevant now. But the reason we chose Petrucci is because of the level. There are a lot of different books out there, but some of the books are a little bit too easy. That is, if you go to UC, like UCLA, they use a high level book that is an honors or majors level. So if you're a chem major, then you want a more serious book. And let's say if you're a bio major taking chemistry, then you probably don't want a high level book. But they use a high level book there. And so this book is like a chem honors level book. And so it's pretty high level, not the highest level. Because the highest level would require calculus in the class, but it's good. This book is expensive though. Did anybody buy this? Bookstore is going to be sad. Nobody bought this in the morning class either. This book is like $200, something like that. $300? Wow. Okay. No. Okay. You can find a used copy of this book pretty cheap. I think I saw one yesterday or the day before. What's that? Yeah, or PDF. I'm not supposed to say anything about those, but yeah, they're PDF copies floating around. But I saw a used physical text. I think it was like $5. I don't know what condition it was in, but it's not that expensive because it's getting old. In addition to the textbook, I recommend getting this. This is the Complete Solutions Manual. Well, it should say almost complete because there are some problems missing out of this. But this is nice to have because this has the worked out homework problems. Almost all of them. Some of the solutions are wrong, unfortunately. They made some mistakes in here. We'll probably talk about that when we get there. Some are obvious, some are not so obvious. But some schools, some schools don't want students to have the Complete Solutions Manual. When I transferred to UCLA, most of the courses I took there had the Complete Solutions Manual. So if I took a math class, Complete Solutions Manual. Took this other class, Complete Solutions Manual. And I think the thinking was they didn't really care if you had the complete worked out answers to every single homework problem in the book because the tests were not like the homework, or not like the lecture. Actually, I shouldn't say that. That's too broad of a generalization. But I should say like 90% of the tests were like the homework or were like the lecture. 10% of the tests were nothing like the homework or nothing like the lecture. They're like beyond, so another step above. And so it didn't matter if you had the Complete Solutions Guide for the homework because the test is going to be harder. Well, harder in one way, but maybe not, so hard in another way. It's still related. Like when you look at a hard problem, it's just like your basic problems kind of interweave together. The analogy that I think of when I'm thinking about studying chemistry or learning something new is like this. When you first start out, let's say if you're driving or riding or walking somewhere and it's in an unfamiliar city, and so you're looking at the directions, take a left turn here, take a right turn there, and so you're following this path that's set out for you. Well, that's the same thing with the homework problems, The homework problems, like I remember sitting in on this one Chem 4 instructor, they're saying, okay, step 1, gram to mole. Step 2, mole to mole. Step 3, mole to gram. Every single problem, you follow that path, right? But what if the step 3 is different? That's a deviation from the path. Well, those deviations are much easier to handle if you have it memorized. So, for example, if you have the route, let's say you're driving from point A to point B and you have that route memorized, then you don't have to really think about that. What step, where do I turn right? Where do I turn left? You already know where to go. And then you can start, you start looking at these side streets or whatever. And you like, there's something interesting down this way. Maybe I'll check that out sometime. And so that's the kind of level you get. And so a lot of people don't like having the solutions manual because they think, oh, this is just memorization. All you're doing is you're just memorizing the steps and solving the problem. Well, I don't think that's exactly correct. The way I think about it is, once you have the basic path down, then you can start exploring to see how these things are intertwined. And I think that the advanced problems, the 10%, are just simple basic problems that they have one, left turn here instead of right turn there, that kind of thing. And so it's not a big deal once you're familiar with the path. And so we'll talk more about this later. But that's a level. So it's like a UC level book, which is good. Here's some SLOs, student learning outcomes. Skip those. Read about it. I assume everybody has a prerequisite for this course. Otherwise, you can't register, I think. For the required materials, the textbook, it doesn't have to be the 11th edition. If you have the 10th edition, the 10th edition, 11th edition are practically the same. Even the 9th edition. I think that the 10th and 11th have the same homework set. I think the 9th is a little bit different. So you have to be careful with that. But the earlier editions, like mine, I forgot what edition mine was totally different. When I look at my Petrucci versus this Petrucci, wow, mine was pretty basic. It wasn't on honors level. It was just a regular text. So at some point in the progression, he made the book more and more rigorous. Okay. We also have the lab manual. The lab manuals is this plastic shrink wrap package, just a 3-hole punch paper. I think somebody had it. They just showed it to me. But it's pretty inexpensive. Oh, there. That's it. The green cover. How much was it? Okay, that's reasonable. 15. Just get the latest version. If you have an older version, that's fine too. The experiments, they haven't really changed. You'll need a non-programmable calculator. I like this one, Casio FX115. Well, I really like this one because it solves quadratics. Actually, it solves cubic equations, third-order equations, quadratics. And so this is a big help, especially in Chem 1B. In Chem 1B, you have to solve a lot of quadratics. In Chem 1A, not so much, maybe one quadratic. So we could use the quadratic formula, but pretty soon, quadratic formula just eats up time. You don't have that much time. So it's nice to have something that solves it pretty quickly. But if you already have a scientific calculator, then just use that. We'll also want a quad-ruled notebook for the laboratory. So, let's see, I have one here. Just a comp notebook with sewn binding, and it's nice to have it graph paper ruled. Here we have table of contents, the 10 experiments this year. And then they just wrote the procedure, the observations. So this is what we're going to use for a lab notebook this semester. If you can't find quad ruled, you can use college ruled as well. This is college ruled here. It's acceptable too. This is a college ruled notebook here. So all these are from past Chem 1A classes here. Safety goggles, the visor goggles are pretty nice. In fact, after the shutdown, a lot of students didn't come back to pick up their goggles. And so we have a lot of used goggles. So if you need a pair and you don't mind using the used pair, then you can get these for free. I don't know how many we have left. It's a lot of students who grabbed a pair last semester. Okay, then I have this optional required. This is optional here at El Camino, but it would be required at a place like UCLA. Actually, items 2 and 3 would be required. So you might as well get used to it. A lab coat. Lab coats are required. When I was a student, I didn't have to get a lab coat until organic chemistry at UCLA. And the type of lab coat I had to get was 100% cotton. It was, at the time, it was $70, you know. In those, nowadays it'd be more like a $200 lab coat or $150 lab coat. But for this class, Chem 1A, you can get by with a $15 lab coat. In fact, that's what I have now. My $70 lab coat's just too beat. So I replaced it with a $15 Amazon lab coat. The difference is my Amazon lab coat is a synthetic material, which is potentially combustible. So you have to watch out for fires. That's it. The reason they wanted people to have cotton is because those synthetic materials are much more flammable than cotton. So, yeah. That's good just to protect your clothing. Otherwise, wear clothes you don't really care about in lab, which I normally do. The other thing that's required at UCLA are nitrile gloves. These are optional here, but it's a good idea to get used to wearing gloves while working in the laboratory, since everybody does. Nitrile are more comfortable than latex, but it doesn't matter. Nitrile also offers better protection against chemicals than latex does. You can buy nitrile gloves at many different places. Okay, this is all posted on Canvas, so I didn't make hard copies of this. But the required assignments, there are going to be no dropped exams and no dropped labs, so all the assignments are going to be required. If you do miss a lab, we'll try to make it up. If you miss an exam or you're going to be absent, then we'll have to figure out how. We'll take that case. But this class consists of 3 midterm exams, each worth 100 points, so that's 300 points. And then we're going to have 14 homework assignments. The homeworks are 10 points each, 140 points of homework. Quizzes, these are just going to happen. In fact, we're going to have a quiz tomorrow. So these are going to just happen like maybe each week. The quizzes, the point on quizzes will vary. So tomorrow's quiz, what is it going to consist of? It's going to consist of nomenclature. What are the most common acids, you think? Yeah. What are the most common hydrogen-based or proton-based acids that you think? Hydrochloric acid. Yeah, that's probably number one. Hydrochloric acid. And so the quiz is going to be like this. I'm going to tell you hydrochloric acid. You're going to tell me the formula. And so what is the formula for hydrochloric acid? HCl. Okay, this quiz is going to be memorization, and it's either going to be right or wrong. There's going to be no partial credit on this. And so you get HCl or 0, even if you're close. So hydrochloric acid, what else? Hydrofluoric. Hydrofluoric. Fortunately, hydrofluoric acid is not so common. Why do I say fortunately? Well, hydrofluoric acid, is it a weak acid or a strong acid? It's a weak acid. What else? What's the most common weak acid that you can think of? It's not hydrofluoric acid. You know what it is? Acetic acid. Acetic acid is in vinegar. People eat this stuff. It's in salad dressings. And yesterday I was at the store and somebody was looking for salt and vinegar chips. not salt, but salt and vinegar. They found them. So. But you would not want to eat hydrofluoric acid. Even though hydrofluoric acid is sour, it's weak acid, you stay away from hydrofluoric acid. So for example, if I spill a little bit of strong acid, HCl, on myself, okay, it's going to sting. I'm not going to worry about it. If I spill a little bit of hydrofluoric acid on myself, I worry about it. I worry about it not because of its acid properties. I worry about it because it has other chemical properties. You know what one chemical property of hydrofluoric acid? I'm sorry? Well, it does more than change the color of his skin. Take a look at, if you want to see gruesome pictures, take a look at hydrofluoric acid burns online. I mean, if you look at vinegar burns, no big deal, right? Vinegar spilled with acetic acid, no big deal. But when you look at hydrofluoric acid burns online, they're really nasty. And I'll probably show some. I'll probably show some when we get to the goggles part, because you can see what happens when somebody gets hydrofluoric acid in their eyes. It's nasty. But the other chemical property of hydrofluoric acid is it loves calcium, and it loves to precipitate calcium fluoride. And so they say that, I haven't experienced this, but they say that you spill some hydrofluoric acid on your skin, it burns a little, like a weak acid, but it penetrates the flesh. And then when it hits the bone, then it's excruciatingly painful as it precipitates out calcium fluoride. And you can't wash it off once it hits the bone, right? And so they use hydrofluoric acid in like etching semiconductors, like silicon chips. And so when I was at UCSB, sometimes I'd go into the electrical engineering department. At the electrical engineering department, they had this wall, the Wall of Horrors. And the Wall of Horrors had pictures of accidents, on there. And one of the accidents is a hydrofluoric acid burn. And on the wall, they have a hydrofluoric acid injection kit. So if you spill hydrofluoric acid, you're supposed to inject yourself with, I think it's calcium. It's some calcium salt with some organic anion. I forgot which one. And so you inject yourself with the calcium, and the calcium hopefully will eat up the fluoride before it causes damage. And so hydrofluoric is not an acid that we're going to be working with in this class. And so what else? Acetic is one. Acetic is, what's the formula for acetic? HCH3 is the formula for methane. But sometimes they call that acid. It's a very weak acid. HCH3 would be the same as CH4. There are two common ways that the formula for acetic acid is written. Either one's fine. Yeah. This is just, during the break, or, I don't know when you took intro chem. During that time, it's easy to forget the stuff. Since it's so easy, I forget things all the time. My memory is awful. So, when I transferred to UCLA, they have something called transfer orientation. During transfer orientation, they said your GPA is going to drop by 1 unit. So I was prepared. I said, well, maybe the average student's GPA is going to drop, but not mine, because I'm going to make sure my GPA doesn't drop by studying extra hard. So I studied extra hard, but still didn't do so great. My first quarter at UCLA, I took this class called Chem, physical chemistry. It's like between physics and chemistry. Chem has a bad reputation failing students, Chem majors out of it. And so at the UCLA bookstore, they sell bumper stickers that say, "I passed P-Chem." I never bought one, even after I passed. But one of my students went to UCLA and bought one of those bumper stickers and gave it to me. So I still have that bumper sticker. I never put it on the car. It's too embarrassing. But anyway, I didn't do so well on the first test. And that made me rethink how I studied, because when you spend all your free time studying and you do poorly, then something's wrong. Right? And so it turns out my score was like pretty bad, like failing score. But the student next to me got the high score. How did they get the high score? And so I started talking to him. And, figured out how he studied. But that changed how I studied completely. And so I'm not going to go into all the details, but one of the things I did was, somebody always asked me, "Is there a study guide for the exam? Are you going to have a study guide?" And I don't have a study guide. Like, you should know this, and this, and this. Although, to be fair, I do give old exams out, so it's not going in totally blind. You see what the format is and types of questions. And the old exams often look very similar to what I give anyway. But there's no study guide, because my philosophy is this. Your notes should be your study guide. And so what you want to do is you want to take as complete a set of notes as possible. And so when I was a student, I'd take a complete set of notes, and then I reviewed those every day. And since I reviewed those, and the notes aren't like the book, like it'd be too hard to memorize everything in the book. But everything in the notes, if you do it day by day, it's like walking the same path. Pretty soon you don't even have to think about it. Pretty soon you have it all memorized. And even if your memory is not so great, like me, I had it memorized. So when the time came for the exam, I had everything memorized. I knew everything. And that's just by repetition. So think about, if you're during break, if you're going through this list every day, don't you think it'd be so easy? Acetic acid, if you looked at it every day, it'd be really easy. You'd know what the formula is. You wouldn't even have to think about it. It'd just automatically come up. It's like motor memory. And so acetic acid, oh yeah, that's easy. HC2H3O2 or CH3COOH. Those are two ways. Either way is fine. Right? But it's motor memory, because every day you're looking at the same thing. It's like walking the same path. Pretty soon it becomes boring. You start looking for new things. What's another acid? That's common. What's that? Sulfuric acid. So what's the formula for sulfur?
HSO4.
Oh,
HSO4.
H2O. Close. But farther, you're getting colder. HSO3 is getting colder. HSO4 is better. But what is it? H2SO4. We call this a diprotic acid, 2 hydrogens. It's a very common acid. What else? Nitric acid. It's a very common acid. What's the formula for nitric acid? HNO3. Let's try to put two more. Hydrobromic is common, but we don't really use any hydrobromic acid. Phosphoric we use. Phosphoric acid you'll find like at Home Depot or Lowe's. They use phosphoric acid in rust remover. What's the formula for phosphoric acid? H3PO4. Good. This one, one of the first lab experiments we're going to do is titration. And this is the acid we're going to use in day one of our titration. It's oxalic acid. What is the formula for oxalic acid?
HC2H4.
HC2H4. Close. Half of it's correct. Well, less than half. 1/4 of that's correct. H. Okay. Yeah, there are different ways of writing this one also. HO2C2O2H. This is what we call a condensed structural formula. This is a bit more of a pain. So most people say H2C2O4. Or you could write it like this. HOOCCOOH. Hook, something like that. To remember. Any of these are fine for the formula. All right, so the quiz is going to be like this. Quiz is you're going to have to write the formula. I'm going to give you the name. This will be tomorrow's quiz. In fact, this will be exactly tomorrow's quiz. So see if you can memorize those. Or it's just refreshing your memory, I think. How many questions are going to be on the quiz? 1, 2, 3, 4, 5, 6. The questions are going to be exactly this. You need to know these 6 acids formulas, and that's it. There's not going to be anything additional beyond this for this. So it should be straightforward. Well, now I know we definitely don't have enough room for everyone. So unfortunately, I can't accommodate all the people who are trying to add. I know that. Too bad. We're limited by how many lab stations we have. And so I'll have to grab another chair. Let's see. Well, go ahead and start. The quizzes are a total of 50 points. This quiz is probably going to be like 30 points. Half a point each. Something like that. Okay, we're going to have labs. Now, you see the lab and the lecture are 2 separate courses. So, versus here they're combined. And so what the UCs and CSUs have forced us to do is they forced us to add this stipulation here. Because if you look at the total points for lab, we have 11 labs and reports, it's going to be 165 points. 2 formal lab reports is 60 points. Lab technique is 10 points. So it's about 200 and something. So it's about a little more than 20% of your grade. So some people think, well, if the lab is only worth about 20%, then I'm going to skip all the labs. Because labs is a lot of work. You have to be here for a lot of hours. Monday and Wednesdays, we're here for 3 hours, right? Plus each day. And so there are people who just skip lab, thinking that they're doing fine in lecture, they're doing well on the exams, the homework, the quizzes. And so they don't take lab seriously. Well, UCLA and the UCs and CSU system in general make us require that regardless of your overall course percentage, you will not pass this class if you fail lab. And so they don't want anybody who's failing lab to continue on to transfer. And therefore, you could be getting an A in lecture and a D in lab, but your overall course grade will be a D regardless of how well you're doing in lecture. And so just be aware of that. It's critical that you make the labs and you don't miss those. Okay, anyway, the grade cutoffs is going to be 88% for an A, 78% for a B, 65% for a C. So this is already kind of curved in that sense. This is just based on past performance, past classes. If you have any special needs or requests, there's a special resources center. They can work out accommodations, or you can talk to me for any special accommodations that might be required. Changes, students will be notified. I used to do it by Piazza, but Piazza is requiring a fee, so I'm not going to do it. It's just by Canvas. So I forgot to delete that or change that. In-class announcement. Okay, a word on cheating here. Academic honesty is mandatory. They have different philosophies. Like when I was at UCSB, some of the professors just didn't care in their Chem 1A class if students were cheating. They didn't care because they figured, they're going to be caught eventually. They're going to be caught sooner than later because as they move up to higher and higher level classes, it's pretty apparent who doesn't belong there. People who got there by cheating aren't going to have the necessary foundation to successfully complete the class. And so they're pretty much weeded out in the next class. That's what they figure. Other professors there were really on top of it. You have to show your ID. I remember UCSB, one student was trying to take the test for their friend, and they were caught. And that student started running out the door. And then after that student, the TA was running after them. And then after the TA, the professor was running after them. This was funny. A little comedic. But obviously, and so it can only get you so far, is what they're thinking is. I have some kind of intermediate thing. So before it gets to this point, hopefully you don't get to this point. Hopefully what you can do is you can get help in other ways. If you need help, there's free tutoring. At the library, there's a long-time tutor there. That tutor is actually taking Chem 1A from me years ago. I was familiar with the course. There's the MESA program. They have Chem 1A facilitators there. I'll announce it later on. There are some online resources. Our books, publisher, they have some practice quizzes, this kind of stuff online. Khan Academy, etc. There's a bunch. And other textbooks. Are you guys familiar with the student study room over here in the hallway? There's a student study room with a small library. In the small library, they have other general chemistry books. Maybe, this is an honors level book, but they'll have some standard level books that might be easier to read. And so you could supplement the reading with other textbooks. That's what I did all the time. And then some notes about studying, my philosophy on studying. One of the things that student next to me did was, that got the high score, was he did all the homework problems. And I thought, how is that possible to do all the homework problems? Some of the homework problems were taking me 2 hours, and I still didn't figure out the answer. That's only one problem. But I finally figured out how he did it. How he did it was he had the complete solutions guide. So if a problem was taking 2 hours, that's a waste of time. If a problem is taking 1 hour, that's a waste of time. You know, if you're not getting it, obviously you want to try first. But if you're not getting it within a reasonable amount of time, then that's like, okay, what did you do over the summer? Well, I went to study, the forest in the Sierra Nevada over the summer. Well, what did you learn? Well, I only looked at one tree in the entire forest for the entire 2 months or whatever it was. That's like looking at one problem. If you spend all your time just looking at one problem, are you ever going to learn about the forest? If you're spending your whole summer looking at one tree in the forest, then you're missing out on the entire forest. So what this person did was they would read the problem and then try to figure it out. If they couldn't figure it out, then they just read the answer. And so read the problem, read the answer, read the problem, read the answer. And eventually what that does is it exposes you to the whole forest. And the whole forest would be all these problem solving methods, all these variations in problem, all the variations in the trees. It exposes you to that. And then what you do is once you know all those variations, then you can link things together. Well, that is, you can see how they're intertwined. And so this is why I recommend getting this. Although for a long time we weren't able to sell this to the students because a lot of professors thought this was cheating, just looking at the answer. But I don't, especially if you're learning a new topic. If you're learning a new topic, you're trying to cram like 30 years knowledge into a semester. It's not easy to do. And so you're trying to learn from experience. You don't want to reinvent the wheel each time. You want to learn from other people's experience. And then what you can do from there is you can build up. If you got the wheel, then maybe you can build a bicycle, or maybe you can build a car or something like that. Okay. So you can download the PDF here. Syllabus. Let's take a look at the syllabus next. So today we're going to jump into chapter 1. Actually, I'm not going to be able to finish it, most likely. Chapter 1 will complete it over here. And so this week we're covering chapter 1, 2, and starting 3. And then we have a holiday on Monday next week. We'll go through chapter 3. But we aren't doing lab until Wednesday of next week, February 22nd. We're going to do experiment day. For experiment day, you aren't going to need safety goggles or closed-toe shoes or lab coat. So we aren't going to need safety goggles until February 27th, third week. On Monday, we'll start the titration. Here we're using oxalic acid. So we're going to titrate oxalic acid with sodium hydroxide. That's day 1. Day 2, we're going to titrate an unknown acid with sodium hydroxide. And we're also starting chapter 4 here in this region. Our first test isn't going to be until the 4th week. Our exam days are going to be on Wednesdays here. And so we'll have the entire lab period for this exam. So it's 3 hours. The exam won't be a 3-hour exam. It'll be a lot shorter, so you may finish early, or you may not. You might want to just review your answers, double check your calculations, that kind of stuff. For homework, I'm just going to collect homework on exam days. And so the homework, I'll collect chapters 1 through 4 homework on this day. When I grade the homework, I just look, did you try it? If you attempted every problem, then you'll get full credit. And so in theory, it should be easy to get 100% on the homework. Just try every problem, show some work. You can even just copy. If you have the complete solutions manual, you can just copy the answer. I don't mind if you copy it by hand. I don't want to see photocopy. Some people just photocopy it and cut it and put it in there, turn that in. I just want to see, because at least if you've seen it before, I think that'll be better than leaving it blank. Okay, some other experiments. So 14 will need goggles, 17 will need goggles, 18 goggles. In fact, all these experiments will need goggles. Okay, exam 2 is going to be at the end of the 8th week. This will be 5, 6, and part of 7. 7 is a long chapter, so we'll kind of split it up. So that's why I call it 7, 8 there. 1, 2. Spring break. Then when we come back from spring break, we'll have another exam 4 weeks later. Exam 3, May 10th. This will be the second half of 7, 8, 9, and 10. These could change, depending if I fall behind. The exam dates won't change, though. So if I fall behind, it'll just alter what material's covered. If I fall behind, the exam dates are always fixed. The lab dates are the same. Those aren't going to change. And then about 4 weeks later, we're going to have the final. And so we aren't going to have the exam 4 to cover this last part. On the final exam, I'm going to split the final exam into 2 days. So our lab day is 3 hours, our lecture day is an hour and a half. And so on part 1 of the final, we'll probably have comprehensive, all chapters, multiple choice kind of thing. And then on part 2, the hour and a half of the regular lecture day, we'll probably have some free response questions. There's going to be a slight bias for the latter material. That is, what we haven't covered, chapters 11, 12, and 14. Slight bias, but still comprehensive. It'll still cover everything from the beginning to the end. The quizzes, those are just whenever. We have some time, we'll throw in a quiz there. Okay, any questions on this, the schedule? All right, so I want to jump into the material here, chapter 1. I have the e-text, and also the hard copy here. Okay, chapter 1 deals with the scientific method, properties of matter, classification of matter. Matter is properties of measurement, basically. Density, percent composition, uncertainty, and sig figs. Actually, there's a lot more to this chapter. One of the main topics of this chapter that's missing is problem solving methods in chemistry. The main problem-solving method that we use, or the tool that we use, is dimensional analysis. So a lot of this chapter is focused on dimensional analysis here. But let's go ahead and review some of the basics here, and then we'll talk about some of the more advanced concepts. There's no fixed scientific method. The scientific discoveries that are made serendipitously, just by chance. Others, depending on what course you have, will have a different set of steps. Even Petrucci has a slightly different set of steps than what I use. But, as far as the day-to-day, okay, you're working in a lab, you're doing science, you go in the lab, what do you do every day? So this is the type of stuff that I did every day. What do scientists do? Scientists observe nature. Chemists observe matter. They spend a lot of time looking at matter, the physical material of the universe. What do they want to understand about matter? Well, they want to understand the properties of matter. That's what we're most interested in, the properties of matter. So, for example, silver versus gold. Silver and gold have different properties. Some of the properties are somewhat similar, like they're both metals, they're malleable, ductile, and conduct electricity. Other properties are a little different. Silver tarnishes a lot easier than gold. So, to understand the properties, we want to understand what it's made of, the composition. And so gold's made up of protons, neutrons, and electrons. Silver is made up of protons, neutrons, and electrons. And so why the difference in properties? Helium's made up of protons, neutrons, and electrons too. Why the difference in properties? And so it's not just composition, but we are also interested in how things are structured. How are those protons and neutrons structured and electrons structured? That might give us insight into why the properties of some substances differ than the properties of other substances. And so, we're always thinking in terms of this. We're interested in properties and understanding the properties, and to get better insight into those, we look at the composition and structure. And so what we do in science is we just observe. We observe properties, we measure properties, we do that kind of stuff. We try to figure out what the composition is, what the structure is. So, for example, graphite is made of pure carbon. Diamond is made of pure carbon. So both of those are pure carbon. Why is graphite so different in properties than diamond? It has to do with the structure. Diamond structure versus graphite structure is quite a bit different. And so scientists observe nature, chemists observe matter, basically. And then what? And then we look for patterns and trends. If these patterns and trends are somewhat precise, that is, they're reproducible, or they're consistent pattern or trend, then we can come up with a law. So an observation might be an apple falls from a tree. And when they take measurements, they see that this is a pretty consistent pattern. So, for example, it takes a certain amount of time. And this amount of time to fall is reproducible. And with that mathematical precision, what they can come up with is an equation that describes that observation. And that equation would be the law, like Newton's laws of motion. Apple falls from the tree. But, the law is very good at describing the apple falling from the tree. How long does it take? How far does it fall? This kind of stuff. But people will start digging into it deeper, After you've done this for a while, okay, we can make these kind of predictions based on the law, but you start thinking, why does the apple fall? Why is the apple trying to fall, let's say, to the center of the earth? Why doesn't it fall up? And then we might hypothesize something like gravity, or come up with gravitational laws. There's something called gravity pulling it to the center of the earth. But ultimately, we want something deeper description of what's happening there. And ultimately, we'd like that theory. Do you know what the theory is? Apple falls to the ground. We come up with laws of motion. Something called gravity. Do you know what the theory is? It came from that. And so this is the development of the theory, and the theory is called the theory of gravity, or actually a little bit beyond that. It's called the theory of general relativity. Have you heard of that? Space-time, all this. Yeah. And so from that, we developed the theory of, but we don't have to go all the way to the theory of general relativity. We can use the laws of motion to send people to the moon. You don't necessarily need to know that. And so let me give you some examples here. When we look at laws, typical laws, there are two types of laws. One type of law is based on empirical data. Empirical, what that means is it's from observation. So this is a law that's derived from observation. And so it's called an empirical law based on empirical formulas, which describe the pattern, mathematical pattern. The other type of law comes from theory, and so it'll be theoretical. So let me give you another example. Another example was, do you know Charles? Have you heard of Charles and Boyles? And what did those guys do? Charles, Boyles? They did the gas laws, right? And so from their observations, we came up with a combined gas law, also called the ideal gas law. And so we have the ideal gas law here. That's empirical. The ideal gas law, PV equals nRT, is an empirical mathematical equation. It comes from observations. Charles. But we can also derive the ideal gas law from theory. So if we know the theory is something called kinetic molecular theory. Have you heard of kinetic molecular theory? Kinetic is, when you think of kinetic, what comes to mind? Energy and movement, motion. And so kinetic molecular theory of gases, if we have kinetic molecular theory of gases, we can also derive the ideal gas law, from the opposite direction. We use kinetic molecular theory. What do you think is easier, combining those simpler gas laws to come up with the ideal gas law, or using kinetic molecular theory to derive it? Probably just combining. Empirical probably is the easier way to derive the ideal gas law than theoretical. But both can be done. And in fact, that's what's done in science. In science, we have a two-pronged approach to our study of properties, composition, and structure. And the two-pronged approach is this. If we know the theory, we can figure things out without having to observe them, without having to do any experimental measurements. And so the two-pronged approach is we try to understand the theory as much as possible. And what is the theory of chemistry? Do you know what the theory underlying chemistry is? We have atoms, and we have molecules. What's a theory? Eventually, all these observations lead to a theory. What's that theory called? Yeah, it has something to do, actually, it is. The theory underlying chemistry is quantum mechanics. So you take all these observations, and all these observations lead to quantum mechanics. So if you know quantum mechanics pretty well, then you can, one of the things that theories have to do is, theories have to do two things. Theories have to be a fundamental description of what's going on. So what is the fundamental description of what's happening with the apple? Well, there's distortions in this field, gravitational field or whatever, and it's falling into a well. And so it's a fundamental description, but it has to have widespread acceptance. And so what we'll say here is it's an accepted fundamental description that has general acceptance, or we'll just say accepted, versus a hypothesis. A hypothesis is also a fundamental description, but we can say it's a tentative fundamental description. And so some people are careful about this distinction, other people aren't. And so sometimes you'll hear this, you'll hear this like, my theory on this is this. My theory on who the murderer is this person. But that isn't really a theory because the theory has to have widespread acceptance. That is, you'd have to agree as well, and others would agree. Instead, that would be more of a hypothesis. My hypothesis is this. And so you're just throwing it out there. The hypothesis, well, what you think, but it might not be correct. Normally what has to happen in order to go from a hypothesis to a theory, it has to go through testing. And this extensive testing is people try to debunk that. And so if you come up with a theory, there are going to be people who are going to try to debunk your theory. Say, no, I don't agree with you. I think this person did it, not that person, right? And so this is where the acceptance comes in. Whereas, you really probably should label it a hypothesis. So a lot of people think of a theory being a tentative explanation, but it isn't. The theory's got to be accepted, whereas a hypothesis is tentative. So not only does a theory have to be an accepted fundamental description, but a theory has to predict new, unforeseen observations. And so an example of this I saw like on YouTube, the Large Hadron Collider. Have you heard of that thing in Europe? One of the reasons they built the Large Hadron Collider is because somebody made a prediction based on the theory. Do you know what that prediction was? That there was the Higgs. Have you heard of the Higgs field? Yeah. Higgs boson, something like that. Well, they built that to test that because the theory made this prediction. Now, if they observe it, then that just reinforces the acceptance of the theory. It increases the validity of that. And so things have got to be tested, and this is how they gain acceptance. People are going to try to debunk the theory, and people will try to make predictions and see if those predictions are observed or not. And so this is how it gets widespread acceptance, because in science, there's no scientific police. So if you come up with some bogus theory, there's nobody that's going to say, well, that's illegal, scientifically illegal. It's self-belief. And that's the great benefit of the scientific method. The scientific method is a lot of these bogus theories are eventually debunked because that's just how science works. People are always testing these things. But the theory, let's say if we're looking at the theory of chemistry, quantum mechanics, is quantum mechanics easy? No, quantum mechanics is difficult, and the math is horrendous. When I was taking physics, there was a physics class I took, which dealt with the hydrogen atom, and it was a 2-volume. Volume 1 was over 1,000 pages of hydrogen atom, and Volume 2 was 600 pages of the hydrogen atom. So that's nearly 2,000 pages of hydrogen atom. Now that's a lot of reading about the hydrogen atom. Do you think you could say that much about the hydrogen atom? It doesn't seem like you could say that much, but you can say that much about the hydrogen atom. It eventually got to molecules, the hydrogen molecule, but that was about it there. So when you get to more complex systems, let's say if you apply quantum mechanics to the cell, the math is going to be horrendous. The math is going to be way too difficult to do. So what you have to do is when the math gets hard, you make simplifications. And these simplifications lead to additional error, uncertainty. And so if you oversimplify things, then you run the risk of having errors and the results not as meaningful. And so what we do is we try to do things with theory, because if we know the theory, we don't have to memorize things. So for example, what is the color of chlorine gas? Okay, the color of chlorine gas. Okay, you're going to do it quantum mechanically. You do it quantum mechanically, you figure out, okay, the electrons get promoted to these orbitals, and we have absorption and emission of light. You guys remember that? And let me figure out what energy of light is emitted, and then I can figure out what color that's going to result in. Do you want to do that? No, that's an awful lot of work. That's an awful lot of work versus just observing it and just memorizing it. What is the color of chlorine? It's green-yellow. It's a green-yellow gas. How do I know? I just memorized it. I've seen it before. And so the two-pronged approach is we want to know as much theory as possible because the theory is going to mean that we don't have to memorize as much, but the theory gets too hard. And so we also need to memorize things as well. And so we do our study of chemistry, our understanding of chemistry is going to be based on theory and observation. Observation are just, chlorine's green, yellow. That's an observed fact. That's it. It's kind of memorizing those things. That's it. And so this is our two-pronged approach. We're going to approach things from the observation and the theoretical side, and then try to understand these things in between. So one of the things, and we don't always go all the way through. So let me give you an example of the scientific method. One, observation would be like temperature. If I did the temperature in degrees Fahrenheit versus the temperature in degrees C, these are my observations. At 32 degrees Fahrenheit, do you know what the Celsius temperature is? 0 degrees Celsius. What's special about these temperatures here?
Directly proportional?
Well, it depends. They're directly proportional if I'm looking at a delta T, but if I'm looking at the ambient temperature or the absolute temperature, they're not directly proportional. There's a correction that we have to have. And that correction is plus 32. Plus 32. I'll talk about it in a minute. But what do these two temperatures have? Well, they're the same temperature, but why do you know these temperatures?
Freezing point of water.
Freezing point of water. Water freezes at about 32 or exactly 32? Does water freeze about 32, plus or minus a little bit, or exactly 32? About? So in other words, what I'm asking you is this. How many sig figs are here? Two sig figs. If I have two sig figs, that means that 2 is uncertain because the rules of sig figs is we're allowed one uncertain digit. So 30 is exact. The 2 is uncertain. So if this were 2 sig figs, this could be anywhere from 31.5 degrees to 32.04. Or not 30. Actually, this could be anywhere from 31.5 to 32.4. Now, these would all round to 32. And this would be what we call the range of precision. The precision is, the higher the precision, the tighter the range is. That is, the narrower this range. The lower the precision, the wider this range is. And so that would be the precision there. And then the precision for this would be, okay, it's anywhere from, 0.05 or 0.5. So this would be, water would freeze anywhere from like 0.5 to, well, actually, what would 0.06. Well, anyway, 0 is a bit more tricky, but because we have to go negative. So this would be negative 0.6 to positive 0.4. And so if we round this to the nearest digit, then we probably round it to 0 degrees C. So is that the degree of uncertainty? That is this the degree of precision for this? Water freezes about 0 degrees, or does water freeze at exactly 0 degrees C? About? Okay. Well, it turns out that somebody defined this. And when somebody defined this, that's different because they defined this as the freezing point of water, pure water. And whenever we have a definition, it's exact. And so in this definition, water freezes exactly at 0 degrees C and exactly at 32 degrees Fahrenheit. No more, no less. This is for pure water under normal conditions. And so what that means is, that means there's no uncertainty here. This is exactly 32 degrees, which means it has how many sig figs? Infinite sig figs. And this is exactly 0, which means this is infinite sig figs. It's right on 0. And that's by definition. We know one other one, 212 degrees Fahrenheit and 100 degrees C. This is also by definition because this is defined as the boiling point of water. And so this is not 3 sig figs. Do you know how many sig figs this is? Infinite. It boils exactly at 212, it's supposed to, and 100, exactly at 100 degrees. And so this is the boiling point of pure water. So these are some observations. We didn't have to take any measurements. If we take measurements, then there's uncertainty associated with those. But with definitions, then we know that this is how it's defined. Then when we look for patterns, we typically graph things. So if I graph the temperature in degrees Fahrenheit on the y and temperature in degrees Celsius on the x. So if I'm at 0 degrees Celsius, I'm at 32 degrees Fahrenheit. And if I'm at 100 degrees Celsius, I'm at 212 degrees Fahrenheit. So this will be 212. Here. Okay, 2 points define a line, 3 points define a curve. So I'd have to take one more. This could be linear, that is a straight line, or it could be non-linear, that is a curve. It turns out it's linear, a straight line. So this is the graphical pattern of the temperatures here. Now, a law is just a simple mathematical equation defining this pattern here. So if I have a straight line, then a straight line fits the mathematical equation y equals mx plus b. So y is the temperature in degrees Fahrenheit. So the temperature in degrees Fahrenheit is equal to m, the slope. The slope is going to be delta y. So delta y will be 212 minus 32 degrees Fahrenheit over delta x. Delta x is going to be 100 minus 0 degrees Celsius. So that's my slope. Times x. X is going to be the temperature in degrees Celsius plus the y-intercept. The y-intercept is going to be 32 degrees Fahrenheit. And so I come up with this equation here. Temperature in degrees Fahrenheit is equal to 9/5. 9 would be in degrees Fahrenheit, 5 would be in degrees Celsius, times the temperature in degrees Celsius plus 32 degrees Fahrenheit. Does this equation look familiar? A lot of people memorize this, but in simpler form. Degrees Fahrenheit is equal to 9/5 degrees Celsius plus 32 degrees. So this is an example of empirical equation. Empirical equation comes from observation. Now, can you derive this equation theoretically? You want to derive this equation theoretically? Probably not. But we could derive it theoretically. Because temperature, in theory, is related to what? Temperature. What's the coldest temperature you can get?
0 Kelvin.
0 Kelvin. What happens at 0 Kelvin? Atoms stop moving. The motion ceases. And so what we can do is we can use kinetic molecular theory to derive this equation as well. We aren't going to do that, excuse me, but let's see. So this is enough. We don't have to hypothesize about this. We don't have to theorize about this. We'll just stop here and use this. There's a relationship between Celsius and Fahrenheit. So there are lots of examples of the scientific method. We'll look at some more as we go along. Okay, what time did we start? 1:15. Okay, let's take a break now, and then